One of the most important scientists in the 19th century was Michael Faraday, who made many advances in the area of electromagnetism. One of these was the discovery of the relationship between magnetic flux and something called EMF in an electric circuit. EMF means electromotive force and was coined by early experimenters to describe what makes electricity move in a circuit. The only way they knew up to that point was EMF created by electrochemical cells or batteries. Now Faraday could add the magnetic force as a way of making electricity flow. It's a confusing name because we know that EMF isn't a force. It's a potential difference or voltage, created because charges are given potential energy, which then lets them move. And you remember that electric potential is just the potential energy per unit of charge. They already knew that a current will produce a magnetic field around it. Faraday found that in some cases, a magnetic field could be made to produce an electric field that made charges move. We say that there is an induced current, and this phenomenon is called electromagnetic induction. Our society would be vastly different without it. The way to see induction happen is to get a loop of wire and connect a sensitive ammeter to it. This is sometimes called a galvanometer. If any current flows through the wire, the ammeter will measure it. If a magnet is moved towards the loop, the ammeter shows that a current has started to flow. If the magnet is stationary, there will be no current in the loop. But if the magnet is moved away again, the current starts up in the opposite direction to when the magnet was moving towards the loop. So it's not enough for there to be a magnet near the loop, it must be moving for there to be a current induced. If a moving permanent magnet can induce a current, what about an electromagnet? In this experiment, we use the apparatus shown in the figure with two conducting loops close to each other but not touching. If we close switch S to turn on a current in the right-hand loop, the ammeter will suddenly and briefly register a current, an induced current, in the left-hand loop. If the switch remains closed, the current stops flowing and no more is observed. If we then open the switch, another sudden burst of induced current appears in the left-hand loop, in the opposite direction. So we get an induced current from an induced EMF only when the current in the right-hand loop is changing, either from being turned on or turned off. There's none when the current is constant, even if it is large. The induced EMF and induced current in these experiments are apparently caused when something changes. But what is that something? Faraday found that it was the magnetic flux. But why do we talk about induced EMF rather than just induced current? The amount of induced current must depend on the resistance of the circuit we connect. So instead, we look at the induced EMF or voltage because that is what will occur whether there is any complete circuit or not, and no matter what the resistance of that circuit might be. So if we connect a circuit with a resistance to our induced EMF, then we can use Ohm's law to find the current. So the relationship Faraday found was that the EMF induced in a loop is equal to the rate of change of magnetic flux through the loop. The minus sign indicates that the induced EMF makes a magnetic field opposing the flux change. This is a result of the law of conservation of energy and is summed up in Lenz's law, which we will talk more about later. So to create an EMF, we need a changing magnetic flux. There are three ways we can make that happen. We can change the magnetic field strength. With permanent magnets, we can move them towards or away from the coil. With electromagnets, we could turn them on or off or vary their current. The second thing we can do is change the area of the coil. This diagram shows an example of this. A circular coil is stretched out until all the wires are horizontal. That would reduce the area that flux can get through to 0. This picture also illustrates another way to think about how much flux is going through a loop. You could think, how many dots or crosses could I see through that loop? Then you can think about whether that number is changing or not. In this example, you could see if the coil was initially a circle, you'd see quite a number of crosses through it, but as it gets stretched out until those wires are touching, gradually you would reduce the number of crosses that you could see until eventually you can't see any at all. The final way we can change the flux is to change the angle of the loop within the magnetic field. This is the way that nearly all generators use, and so we'll look at that in more detail later. Now, just in case you're confused about the units, let's look at whether it's possible that volts could be the same unit as Webers per second. Neither of them are base units in the SI system, so they're combinations of base units. When you look them up, you will find that volts actually equals kilograms meters squared per second cubed per ampere, while Webers equals kilograms meters squared per second squared per ampere. So luckily it all fits. Now let's try a few questions about Faraday's law.